Bismillah ar-Rahman ar-Rahim. This video is about the Jordan canonical form for nilpotent matrices. We have a matrix L that is of size n by n. It is nilpotent, which means that there exists a positive integer k less than or equal to n, such that L to the power k is the all zero matrix. The smallest positive integer k that gives this result is the index of matrix L. If we raise L to any smaller power, we don't get the all zero matrix. If the index is 1, then L itself is equal to the all zero matrix, and this is not a very interesting case. So it is assumed here that the index is an integer that is greater than or equal to 2. What is the goal? L is not diagonalizable. Why is this the case? All the eigenvalues of L are equal to 0. If L has an eigenvalue that is not equal to 0, then L to the power k will have a non-zero eigenvalue. But L to the power k is the all zero matrix, thereby indicating that all eigenvalues of L must be equal to 0. What is the algebraic multiplicity of the eigenvalue 0 for matrix L? This is equal to n, because L is an n by n matrix. What about the geometric multiplicity of the eigenvalue 0? The geometric multiplicity of the eigenvalue 0 of matrix L is the dimension of the null space of L minus 0 times the identity. That's the dimension of the null space of L. Note that if we take the case in which the index of L is greater than or equal to 2, then the null space of L to the power 0, which by definition is taken to be the identity matrix, this is just the all zero vector in n dimensions. This will be strictly contained in the null space of L, which is strictly contained in the null space of L square. And we have strict growth of the null space till we reach L to the power k. Now, the null space of L to the power k is the whole n-dimensional space, and the null space will then remain the same. If the index k is 2 or more, then the dimension of the null space of L is strictly less than n. For a matrix to be diagonalizable, every eigenvalue must have the same algebraic and geometric multiplicities. Therefore, if the index of the matrix is 2 or more, the matrix is not diagonalizable. Knowing that L is not diagonalizable, the objective is to obtain an invertible matrix P such that P times L times the inverse of B is a matrix that is very close in structure to a diagonal matrix. We cannot have here a diagonal matrix. Can we have, for instance, a matrix in which we just have non-zero entries on the diagonal above the main diagonal, which sometimes is referred to as the first super diagonal? Let's go back to our matrix L. The null space grows and then remains the same. The range of the matrix, on the other hand, shrinks till we reach L to the power k, which is the all zero matrix, whose column space is just the all zero vector. Let omega j be the intersection of the null space of L and the range of L to the power j. J is an integer that can be 0, 1, all the way to k. K is the index of L. What is omega 0? That's the intersection of the null space of L and L to the power 0, which by definition is taken to be the identity matrix of size n by n. This range is the whole n-dimensional space, so this is the null space of L. Omega 0 is the null space of L. What is omega k? That's the intersection of the null space of L and the range of L to the k. But L to the k is the all zero matrix, and the range is just the all zero vector. This intersection is just the all zero vector. The dimension of omega 0 is the dimension of the null space of L, which is the same as the geometric multiplicity of the eigenvalue 0. Omega k, where k is the index, has a dimension of 0. Because the column space strictly shrinks as we raise L to higher powers till we reach L to the k, then we have the following containment relationship for the omegas. Omega 0 contains omega 1, which contains omega 2, and so forth. What is the dimension of this omega j? To compute the dimension, we make use of the following result. If we have two matrices, x and y, with compatible sizes, the rank of xy, the rank of the product, is equal to the rank of y minus the dimension of the intersection between the null space of x and the column space or the range of y. From this relationship, we know that the dimension of the null space of x intersection the range of y, this is equal to the rank of y minus the rank of xy. Let's use this relationship here to investigate the dimension of omega j. The dimension of omega j, denoted by dj, is the rank of L to the power j minus the rank of L times L to the power j. So dj, which is the dimension of omega j, is the rank of L to the power j minus the rank of L to the power j plus 1. Note that dk is equal to 0 because omega k is just the all zero vector. Define Sj to be dj minus dj plus 1. Note that sk minus 1, using this definition, is dk minus 1 minus dk, but dk is equal to 0, so sk minus 1 is equal to dk minus 1. Our starting point for operating on matrix L is omega k minus 1, which by definition is the intersection of the null space of L and the range of L to the power k minus 1. Note that this intersection here is simply the range of L to the power k minus 1. And we can show this by taking a vector in this range. So take vector z in the range of L to the k minus 1. Because this vector is in the range of L to the k minus 1, this vector can be written as a linear combination of the columns of L to the k minus 1. In other words, vector z can be written as the product of L to the k minus 1 and a column vector, say, beta. If we multiply both sides by L, we get that Lz is equal to L to the k times beta. But L to the k is the all zero matrix. Thus, L to the k times beta is the all zero vector. Lz is the all zero vector. This means that z is in the null space of L. If we start with a vector in the range of L to the k minus 1, this vector is guaranteed to be in the null space of L, thereby indicating that the range of L to the k minus 1 is contained in the null space of L. The conclusion is that omega k minus 1 is simply the range of L to the k minus 1. We can obtain a basis for this range. Suppose that a basis for omega k minus 1 is those vectors w1, w2, all the way to wsk minus 1. Recall that the dimension of omega k minus 1 by definition is dk minus 1, which is the same as sk minus 1, because dk is equal to 0. If we want a basis for omega k minus 1, then we need sk minus 1 linearly independent vectors. Those are the vectors from w1 to wsk minus 1. In this video, I will not focus on how actually those vectors are obtained. Those are a basis for the range of L to the k minus 1. So at least in theory, we can obtain them via the Gaussian elimination. These can be the basic columns obtained via putting the matrix L to the k minus 1 in the row echelon form. Because those vectors are in the range of L to the k minus 1, I can take each one of them. Let's say we start with w1. I can write it as L to the k minus 1 times another vector, say x1. And generally, we can have wv to be written as L to the k minus 1 xv. And here I will put a superscript k minus 1 to indicate that we are operating on omega k minus 1. We have now those sk minus 1 vectors, which will play a very important role in constructing this P matrix. Those are the sk minus 1 vectors from the previous page. Those vectors, when multiplied by L to the k minus 1, those are the w vectors. Those are the basis for omega k minus 1 with dimension sk minus 1. What we do here is that we take those vectors and multiply each by L, multiply each by L squared, all the way to Lk minus 1. And those again are W1, W2, all the way to Wsk minus 1. Here we are constructing the Jordan chain, which, as we will see, will help us achieve our goal. Recall that omega k minus 1 is contained in omega k minus 2. These vectors constitute a basis for omega k minus 1. We complete this basis set so that we have a basis for omega k minus 2. Recall that omega k minus 2 is the intersection of the null space of L and the range of L to the k minus 2. We obtain those vectors perhaps as w bar 1, w bar 2, all the way to w bar sk minus 2. We know that these vectors are in the range of L to the k minus 2. So those vectors can be written as L to the k minus 2 times those x vectors with a superscript k minus 2 to indicate that we are operating on omega k minus 2. And as we did here, we have those x vectors, we multiply them by L, L squared, all the way to L to the k minus 2. Why is the number of vectors here sk minus 2? Recall that we defined dj to be the dimension of omega j, and sj to be dj minus dj plus 1. The dimension of omega k minus 2 is dk minus 2. To have a basis for omega k minus 2, we need dk minus 2 vectors. We have sk minus 1 vectors from the previous step, and so the number of extra vectors needed is sk minus 2, which by definition is dk minus 2 minus dk minus 1. And dk minus 1 is equal to sk minus 1. We have the basis for omega k minus 2. Let's extend it to cover omega k minus 3. How many extra basis vectors do we need? We need sk minus 3, which by definition is dk minus 3 minus dk minus 2. Sk minus 3 is the dimension of omega k minus 3 minus the dimension of omega k minus 2. We obtain those extra basis vectors. Let's say they are w tilde 1, w tilde 2, all the way to w tilde sk minus 3. Those vectors are in the range of L to the power k minus 3. We can write each one of them as L to the k minus 3 times those x vectors. We have those x vectors, and then we have them multiplied by L squared, all the way to their multiplication by L to the k minus 3. And we continue doing this till we have a basis for omega 0, which is the null space of L. Those topmost vectors are a basis for the null space of L. But whenever we obtained any of those vectors, we constructed the so-called Jordan chain by having those other many vectors. The claim is that all those vectors together are a basis for the n-dimensional space. And so those vectors, if we stack them as columns in a matrix, that matrix will be an invertible matrix. We need to verify that there are n of those vectors, and we need to verify that they are linearly independent. Let's focus first on counting those vectors, making sure that there are n of them. How many vectors do we have here? We have sk minus 1. But those sk minus 1 vectors are not enough for our goal. And so we take each vector and we construct a chain of k vectors. For example, if we have this vector x1 with the superscript k minus 1 to indicate that we are working with omega k minus 1, we have x1 multiplied by L squared, all the way to Lk minus 1. Each vector in this collection of sk minus 1 vectors is used to generate k vectors. The total number of vectors generated when we process omega k minus 1 is sk minus 1 times k. Then we extend the basis to cover omega k minus 2. Now we have an extra sk minus 2 vectors. For each vector, we have k minus 1 vectors that are generated. x1, L squared x1, all the way to L to the k minus 2 x1. So sk minus 2 is multiplied by k minus 1, and so on. The total number of vectors that we have is summation j from 0 to k minus 1. Then we have sj multiplied by j plus 1. Sj is this difference, dj minus dj plus 1. Split this sum into two sums. So here is one of them, and the other will be summation j from 0 to k minus 1, j plus 1 times dj plus 1. In this summation, replace j by j minus 1. What will happen is that j now goes from 1 to k, j plus 1 is replaced by j, dj plus 1 is replaced by dj. But recall that dk is equal to 0. We can stop this summation at k minus 1. And from this summation here, we can isolate the term corresponding to j equal to 0. This will be 0 plus 1 times d0. So we have d0 here, and then this summation and that summation, in both, the index goes from 1 to k minus 1. We can now combine them. We have j plus 1 dj minus j dj, and this is equal to dj. d0 is the dimension of omega 0, which is the null space of L. And these two sums together will give us summation j from 1 to k minus 1 dj. But dj is the rank of L to the power j minus the rank of L to the j plus 1. We have a telescoping sum. This summation here will start from the rank of L to the power 1, which is the rank of L. Then the other surviving term is the rank of L to the power k minus 1 plus 1. That's the rank of L to the power k. L to the power k is the all zero matrix, and so the rank of L to the power k is 0. The total number of vectors generated is equal to the dimension of the null space of L plus the rank of L. By the rank nullity theorem, the sum of the rank and the dimension of the null space is the number of columns of the matrix, which is small n. What we have here is a total of n vectors. Are they linearly independent? What we will do is that we will collect those vectors in a matrix Q. We take those vectors first and use them as the rightmost sk-1 columns of matrix Q. Let's call this submatrix Q0. Then we take those sk-1 plus sk-2 that's dk minus 2 vectors, and put them to the left of those guys. Those are the columns of submatrix Q1. Then we take those sk minus 1 plus sk minus 2 plus sk minus 3. That's dk minus 3 vectors, and put them to the left of those guys. Those are the columns of matrix Q2, and so forth. We collect the vectors row by row, starting from the last row, and we put these vectors from right to left as columns in the matrix Q. To check whether those vectors are linearly independent or not, we multiply matrix Q by the n-dimensional vector Z. We ask ourselves, what is the solution to QZ equal to the all zero vector in n dimensions? If the only solution is when all the components of Z are equal to 0, then the columns of Q are indeed linearly independent. So we take matrix Q and multiply it here by vector Z. The bottom sk minus 1 elements of Z are denoted by Z tilde. The previous sk minus 1 plus sk minus 2 elements are denoted by Z bar. The previous sk minus 1 plus sk minus 2 plus sk minus 3 elements are denoted by Z double bar, and so forth. We want Q times Z to be equal to the all zero vector. The trick here is that we will take this matrix equation and multiply it from the left by L to the power k minus 1. We have L to the k minus 1 times Q times Z is equal to the all zero vector in n dimensions. L to the k minus 1 will be multiplied by each column in matrix Q. L to the k minus 1 will be multiplied by those columns here of the submatrix Q0. But what happens when L to the k minus 1 is multiplied by Q1 or by Q2, and so on? L to the power k minus 1 times any vector here which has an L yields L to the power k, and L to the power k is the all zero matrix. Then we have L to the k minus 1 multiplied by those columns. Let's just focus on L to the k minus 1 times x1. What is this product? Note that L to the k minus 2 times x1, this is one of the basis vectors for the null space of L, like all other vectors in the topmost row. If this vector is multiplied by L, then we get the all zero vector. Again, because this is a vector in the null space of L. This means that L to the power k minus 1 times any one of those vectors will give us the all zero vector. It can be checked that L to the k minus 1 times any of those vectors all the way to here will give us the all zero vector. Starting from this equation, what we have now is L to the k minus 1 times Q0 times Z tilde. This is equal to the all zero vector with sk minus 1 zeros. When those vectors are multiplied by L to the k minus 1, we get those vectors. What are these? They are basis vectors. By definition, they are linearly independent. And because they are linearly independent, then the only possible solution to this system of linear equations is that Z tilde is equal to the all zero vector. Our conclusion is that the bottom sk minus 1 elements in vector Z are all equal to 0. The next step is to multiply QZ by L to the k minus 2. What will happen when L to the k minus 2 is multiplied by the columns of submatrix Q2? L to the k minus 2 times L squared is equal to L to the k, which is the all zero matrix. L to the k minus 2 times L x1, and here we have a superscript k minus 2. This is L to the k minus 1 x1. We can rewrite this as L times L to the k minus 2 x1. L to the k minus 2 times x1, this is a basis vector for the null space of L. If we multiply by L, then this is the all zero vector. What if this vector is multiplied by L to the k minus 2? L to the k minus 2 times x1, and now the superscript is k minus 3. This is equal to L times L to the k minus 3 times x1. This is a basis vector for the null space of L. So this multiplication again yields the all zero vector, and so on. The idea is that if the columns here of matrix Q are multiplied by L to the k minus 2, we get all zero vectors, except when L to the k minus 2 is multiplied by submatrix Q1 and by submatrix Q0. Our equation becomes this one here. But we know two things. The first is that those sk minus 1 elements in vector Z are all equal to 0 from the previous step. Our equation is L to the k minus 2 q1 z bar equal to the O0 vector. But L to the k minus 2 q1 gives us basis vectors for the null space of L. And because they are basis vectors, then by definition, all of them are linearly independent. The only solution that we can have is that z bar, those sk minus 1 plus sk minus 2 elements in vector z, are all equal to 0. We can continue carrying out this procedure and show that if we solve this linear systems of equation, the only solution is that vector z is the all zero vector in n dimensions. Matrix Q is invertible. Its columns, which are these vectors that we have here, are linearly independent. And we have n of them. These vectors can be used to construct an n by n non-singular matrix. Recall, our goal is to have matrix L when multiplied by invertible matrix P, and then by B inverse, we get a matrix that is close to being diagonal. Now we have these L linearly independent vectors, and we need to show that if these vectors are used as columns of matrix P, then we will get our desired result. Consider the vector xv superscript j. So this is a vector obtained during the processing of omega j, which is the intersection of the null space of L and the range of L to the power j. J is from 0 to k minus 1. Recall that when we did the processing, we started with k minus 1 downwards. V is from 1 to Sj. Sj is dj minus dj plus 1, and dj is the dimension of omega j. We construct the matrix bjv. This is an n by j plus 1 matrix. We take this vector, here it is, and then we take the vector after multiplying it from the left by L, and then by L squared, all the way to xv multiplied from the left by L to the power j. So we have j plus 1 columns. Let's investigate the multiplication of this matrix by the matrix L from the left. The first column in this matrix here is one of the basis vectors of the null space of L. This means that when L is multiplied by this column, we will get the O0 column vector. If L is multiplied by L to the j minus 1 xv, we get L to the j xv, and so forth. We can write down this product L pjv as bjv times a square matrix of size j plus 1 by j plus 1. When we did the product, the first column is all 0. The first column in this square matrix should be an all 0 column. In this product, the second column is L to the j times xv, and this is exactly the first column in pjv. This means that the second column in this square matrix should have 1 followed by zeros. The third column in this product is the second column in pjv. Our third column here should be 0 followed by 1 followed by zeros, and so on. Matrix L times bjv is equal to bjv times this j plus 1 by j plus 1 matrix denoted by nj. This is a matrix that is 0 everywhere except the ones that we have here on the diagonal above the main diagonal. And this is exactly what we want from this product. In other words, to achieve our goal, we construct matrix P using those matrices bjv. The first S0 columns in matrix P will be those columns. So matrix B01 is just an n by 1 matrix which has this x1 vector. Then we have B02 all the way to B0S0, which has 1 column XS0. Corresponding to each of those n by 1 matrices is an n0 matrix. An n0 matrix is a matrix of size 1 by 1. It has 1 element which is 0. After that, we go to those vectors here, and we use those vectors to construct the matrices B11, B12, all the way to B1S1. What is matrix B11? Matrix B11 will make use of these 2 column vectors. Specifically, B11 is an n by 2 matrix. This column here is x1, and this column is L times x1. Corresponding to each one of those matrices is an n1 matrix. The n1 matrix is a 2 by 2 matrix, and it looks like this: 0, 1, 0, 0. We keep doing this, more of the same. The last submatrix in matrix B is this pk minus 1 sk minus 1, and this comes from those vectors. Pk minus 1 sk minus 1 is an n by k matrix. Here we have s xk minus 1, and then we have it multiplied by L squared, and the first column will be L to the power k minus 1 times sk minus 1. If we have this matrix P, then L times B given our previous result, will be this matrix here with those blocks on the main diagonal. Block nj is of size j plus 1 by j plus 1, and it looks like this. This means that B inverse LP is equal to this matrix here. How many blocks do we have? How many submatrices are used in the construction of P? We have made use of every array here. And how many arrays do we have? The number is equal to the dimension of the null space of L. The number of those blocks is the dimension of the null space of L. What are the sizes of those blocks? We have from 1 by 1 to k by k. So the largest block is of size k by k. Recall that k is the index of matrix L. Although I am not providing here a full algorithm for obtaining the Jordan chains needed to generate the invertible matrix P, I think it is worthy to talk about how we can obtain a basis for the intersection of the null space of a matrix and the range of another matrix. This is relevant to our topic because in obtaining the Jordan canonical form, we obtain the basis for the intersection of the null space of L and the range of L to the power j for j equal to k minus 1, k minus 2, all the way down to 0. So this is a general problem. If I have a matrix A, and let make things general in terms of the size. Matrix A is of size n by n, matrix B of size n by q, and we are interested in a basis for this intersection. Suppose that the dimension of the range of B, the rank of B, is equal to R. Suppose that matrix big Y of size n by R contains a basis for the range of B. After obtaining matrix Y, we can multiply it from the left by matrix A, and then we can obtain a basis for the null space of AY. Suppose that the dimension of the null space of AY is S, and a basis for the null space of AY contains S vectors. These S vectors are Z1, Z2, Z3, all the way to ZS, and these are the columns of the R by S matrix Z. The two steps here are sort of standard. We obtain a basis for a range and a basis for a null space. But our objective is to obtain a basis for this intersection here. The claim is that the columns of Y times Z constitute a basis for the intersection of the null space of A and the range of B. Note that Y times any column in Z is in the range of Y, and the range of Y is the range of B. Note also that if we multiply YZ from the left by A, AYZ is the all zero matrix. The reason for this is that Z by construction contains vectors that are in the null space of AY. The columns of YZ are in the null space of A. Now we have verified that the columns of YZ are in the range of B. Also, they are in the null space of A. To be precise, our conclusion is that the span of those columns of YZ is a subset of this intersection. We are done if we prove that the rank of YZ, or the dimension of the range of YZ, is equal to the dimension of the intersection between the null space of A and the range of B. Since the range of YZ is a subset of this intersection, then the dimension is less than or equal to the dimension of the intersection. If we show that we have equality, then indeed these two subspaces are the same. What is the dimension of the range of YZ? What is the rank of YZ? We can use the formula for the rank of the product of two matrices. The rank of YZ is the rank of Z minus the dimension of the intersection between the null space of Y and the range of Z. Y is a matrix with basis vectors. Those columns here are linearly independent. The null space of Y is the trivial null space, just the all zero vector. This means that this intersection is the all zero vector and the dimension here is equal to 0. The rank of YZ is simply the rank of Z, and the rank of Z is the number of those columns here, which is equal to S. This side is equal to S. The rank of AB is the rank of B minus the dimension of this intersection. What about the rank of AY? Using the same formula, the rank of AY is the rank of Y minus the dimension of this intersection. But the range of Y is the same as the range of B. This means that the rank of AB is equal to the rank of AY. And what is the rank of AY? By the rank nullity theorem, the rank of AY is the number of columns of AY here, which is R, and R is the rank of matrix B, minus the dimension of the null space of AY. And this null space is assumed to have a dimension S. The rank of AB is equal to the rank of AY, which by the rank nullity theorem is equal to R minus S. So what is the dimension of the intersection of the null space of A and the range of B? This is equal to the rank of B minus the rank of AB. The rank of B is R. The rank of AB is R minus S. R minus, between brackets, R minus S, that's S. These two sides here are equal, and hence the columns of YZ are in fact a basis for the intersection between the null space of A and the range of B.